From the acidifying ocean to the citrus fruits we eat, such as oranges and lemons, to the coffee we drink from Starbucks, to the baking powder we use when baking delicious cake, to the soap we use for sanitation, acids and bases are all around us. Better yet, they are all in us. The lung and kidney systems in our body maintain a stable amount of CO2, which allows for the ideal pH in order for the enzymes to work in digestion, metabolism, and much more. Welcome to Chemistry Uncovered, where we uncover the mysteries of acids and bases through explaining in further detail their importance and diving into some basic concepts. Hey guys, welcome back to another weekly episode on Chemistry Uncovered. I am back at you at the Chemistry Uncovered studio, so I hope you guys enjoy this familiar setting. And without further ado, as you guys have watched the last week's video, and if you haven't watched, you should go check it out, last week's video about ocean acidification. I hinted on what this week's video would be with the acidification part. This week's video is acid-base chemistry, right? So we're going to talk about the bonds between acids and base, and we're also going to talk about how they dissociate and the pH scale and equations and the application, the real-world application. This is Chemistry Uncovered, episode 17. Enjoy. So without further ado, right, I want to first talk about why are we learning acid-base chemistry? What is the relevance in the real world, right? Well, first of all, one huge relevance is ocean acidification. If you guys haven't watched it, you guys should check it out. It's episode 16 on Chemistry Uncovered, last week's video. And it basically talks about how CO2 emissions, how when they enter the sea, they acidify the ocean, which decreases ocean, species livelihood and decreases their chance to, frankly, survive. And so we have to do our part to lessen ocean acidification. That's just a small portion of how acid and base chemistry is used in the real world. Some other ways is that, I like to use the phrase acid bases are all around us and in us. All around us, as in there's acids in the real world, such as fizzy drinks, Fanta, Coke, 7-Up, Starry. There's also citrus fruits such as lemon, lime, oranges. There's also vinegar, which is also acidic, and vitamin C, which all of you guys need. And then the bases, right? Chewing gum, a lot of them are basic. Detergent, the detergent you use to wash your clothes, like this. Baking powder, sorry, it says baking powder, but it's baking powder for baking. Soap, when you wash your hands, that's basic. And toothpaste. And in us, as in just a small example, the four main acids in our body are fatty acids, amino acids, ascorbic acids, and also hydrochloric acid. It says fatty acid twice, but it should say hydrochloric acid. So those are the four main ones: fatty acid, amino acid, ascorbic acid, and hydrochloric acid. And also blood pH, right? In order for us humans to survive, we need an equilibrium in the blood pH, which is slightly basic, from 7.35 to 7.45 pH. Right now, these are just numbers to you, but I will explain in the next few slides what they mean, right? Why is blood pH important, you may be asking? Well, to uncover that mystery, blood pH is important because it provides tissues with their necessary oxygen. It also helps the immune system fight off illnesses and diseases. And also it allows peptide protein structure in amino acids, which helps benefit enzymes and the enzyme functionality in your body. So without further ado, I'm gonna uncover this chemistry of acid and bases, right? First off, the first theory that came with the person who coined the idea of acid bases is Svante Arrhenius. I'm sorry if I'm mispronouncing that. He was a Swedish man. He started the Arrhenius theory in 1883. Basically stated that acid produces hydronium in aqueous solution and bases produce hydroxide, OH- in aqueous solution. Aqueous solutions, as you guys see in this bottom depiction, aqueous means dissolved in water, most of the time dissolved in water solution. In the equation, hydrobromic acid, HBr, reacts with water. When it is dissolved in water, it creates hydronium and it also creates bromine minus, right? And so as you can see, using the Arrhenius theory, HBr is the acid which produces H3O in an aqueous solution, and the aqueous solution is water. Likewise, for the base NaOH, when it is dissolved in aqueous solution, I don't have to write water again because aqueous means dissolved in water, right? When sodium hydroxide is dissolved, which that is NaOH, sodium hydroxide dissolves into Na+, but more importantly, for our educational purposes, OH- hydroxide, which means that it's a base. However, there are limitations to this, right? Arrhenius theory doesn't explain how bases without hydroxide still release hydroxide ions to make a basic solution. For example, as you guys see in this depiction, for ammonia, NH3, it doesn't have hydroxide. It doesn't have the hydroxide that NaOH had, right? So how is NH3 basic, when it still releases hydroxide? Well, the Bronsted and Lowry, two different people, both their last names combined, create a definition in which, in short, acids are proton donors, meaning they donate H+ hydrogen protons. Bases are proton acceptors. They accept the protons from the acids. They gain hydrogen ions, right? Also, it's important to note that amphoteric compounds such as water can react as a base or an acid. In the equation shown with ammonia, it's an acid because ammonia is a base, right? And so when ammonia reacts, ammonia being the base, it gains a proton during the process of the reaction. So it turns into ammonium, it gains one more H, which results in the NH4 plus compound. And then also when that H from the acid is donated to ammonia, the acid H2O loses a hydrogen, right? So it turns into hydroxide, which is the conjugate base. Ammonium is the conjugate acid. The conjugate acid is always paired up with the base, and the conjugate base is always paired up with the acid. That's something to remember. Again, the base is always paired up with the conjugate acid, and the acid is always paired up with the conjugate base, right? And so these are just some equations on acid dissociation constants. So if we have an acid with water, it creates H3O plus and A minus. The acid dissociation constant is always products concentration over reactants concentration, right? Liquids and solids do not participate in dissociation constants. It's only aqueous and gas. So H2O is not in the equation, which results in the acid dissociation constant. In order to calculate your H3O plus concentration, if you know your Ka, or your Ka value if you know your H3O plus concentration, right? Usually, you may be asking, there's three variables. How can you calculate H3O plus, right? Usually the A minus and H3O plus are the same concentration because the molar ratio is 1:1. So you can just substitute that as X squared. Same thing goes for a base. The base dissociation constant, Hb plus times OH minus over B. And then for water dissociation, when water dissociates to H plus and hydroxide, hydrogen and hydroxide, the equation is H plus times OH minus equals Kw. And you may be asking, where's the denominator? Well, the denominator for this H2O is a liquid, so it doesn't participate in the reaction, right? Now, you may be asking, knowing the acid dissociation constants, which acids and bases dissociate the most so that they have the highest Ka or highest Kb, right? Because if you know which acids dissociate the most, then it should click, right? It should bond it should bond in your brain. Why, like bond just like these chemical bonds, why these strong acids have such high Ka values, right? It should be like a click moment. Well, the strong acids are HCl, hydrochloric acid, should write HNO3, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and perchloric acid, which is HClO4. The strong bases, which correlate with a high Kb value, is lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, strontium hydroxide, and calcium hydroxide. Essentially, all the group 1 elements of hydroxide, and strontium and calcium, which are group 2 with hydroxide, right? The pH calculations, how do you get pH and how can you determine whether a compound is acidic or basic? Well, you use this chart, this kind of, I would say diamond-shaped chart, with pH plus pOH always equals 14. You have to remember that. And going from branching off from pH equals negative log hydronium concentration. pOH equals negative log hydroxide concentration. Ka for pH is H3O plus times A minus over HA. Kb for pOH is OH minus times HB plus over B. And then Ka times Kb always equals 10 to the power negative 14 equals Kw. And you can derive the pH plus pOH equation equals 14 equation from the Ka times Kb equation. So pause this if you need to take a screenshot for future reference in your classes. But to kind of synthesize, when you calculate the pH value, if the pH is less than 7, it's an acid, such as battery acid, stomach acid, vinegar, tomato juice, coffee. I know a lot of you guys get coffee from Starbucks, right? pH equals 7 is neutral, which is water, and then pH greater than 7 is a base, which is blood, baking soda, chewing gum, ammonia, soap, bleach. And to end off, I want to end with a quote from Vinay Rawat. In the world of acid, act like a base. What does that mean? Well, that means that you have a duty to make this world a better place, as I will end every single video saying, when there's a lot of acids in the world, when there's a lot of problems in the world, act as a base, neutralize the problems, try to do your best to neutralize those acids, to do your best, even in the circumstances when what you guys are faced with, to always persevere, to always act as a base, to always do everything in your power to turn those mistakes, turn those acids into learning experiences to help you learn and to help the pH grow just like how you grow whenever you learn from mistakes. So this has been Chemistry Uncovered. Thank you so much. New video coming out in next week. Stay tuned. Peace out.